Good morning, Aniruddhan.
Hi, Bobby.
So, in the lab, when we were doing experiments for the electronic system thinking course, so there were, I think we have done a low pass filter
Yes,
where there is one,
I think there was a series resistor
correct,
and a shunt capacitor.
correct. So we had one AC source,
Correct.
and then there was a series resistor.
Series resistor and a shunt capacitor.
Yeah,
And I think we completed the loop after that.
yeah.
Correct.
So then we have taken output from here.
Yes.
Let's say Vs. We got some characteristic with respect to frequency also. Now, let's say if I have some more RCs, maybe.
So, in the first case,
Huh?
for 1R and 1C,
Yeah,
I think, we solved it in the time domain. We wrote down the equation for the resistor,
correct,
equation for the capacitor,
correct.
and then found the voltage across the capacitor as a function.
So there was a small differential equation, and we found solution of that.
That is correct. That is
So if I have multiple of this,
correct.
then I may get more complicated differential equation, no?
Definitely, I think so. In
Or
fact,
let's say this is R1, C1, R2, C2,
okay,
R3, C3, and if I want to get now output here,
okay,
let's say if I give a input here,
okay.
this may be a lot of work for me to get
There's
solve
going to be
the.
a lot of work. Correct. No, in fact, even setting up the differential equations is going to be difficult.
That will be 20 minutes job.
20-minute job.
Is there any easier way to, is there any tool available to handle such solutions? To analyze
Okay.
circuits.
See, all I know is I know how to solve linear equations.
Mhm.
Right. So, if you tell me I don't know some variables v1 and v2, if you tell me a v1 plus b v2 is some number, c v1 plus d v2 is some number, I can solve it.
So somehow, if the differential equation can be moved to a algebraic form,
Algebraic form, yes.
then
I know how to do it.
then we are
Correct.
more comfortable.
That's right. That's right.
Oh, how do you transform like that? I have heard about this logarithm.
I like
etc.
this word transform.
Yeah,
I like
it
that
looks
word.
like you are transforming from.
That's right.
This is differential equation, and then that is
Algebraic equation.
algebraic equation.
Correct. Correct. That's right.
That kind of transform, I know logarithm, where multiplication, once you take logarithm, instead of multiplying, you can just take sum of that,
That is
correct,
true.
no?
Correct. That's right.
And then to get back the actual multiplied results, I can take anti-log.
That's true. You know what? I remember when I was in high school,
Huh.
long time ago, maybe more than 25 years ago, 30 years ago. That is what we used to do. We were not allowed to use calculators in exams. When we had to multiply two large numbers for solving a physics question paper or a chemistry question paper,
So there was a log book.
we had a log book. I think it was called Clark's tables.
Yeah,
Right?
correct.
So it was a log anti-log book.
Correct.
We would find out the log for first number,
Yeah.
log for the second number. We would add the two logs and then take the anti-log.
Yes.
That's right.
Yeah, calculators were not that much available at that
Much
time.
available
So-
at that time. Correct.
Correct. So that is one way of transforming, I guess. Huh?
Yes. Yes.
So the transformation or transform that you are talking is something else. Log cannot do this. For
Log
example.
cannot do this for us. Correct. Because log is useful for multiplication to
Correct.
Addition,
Correct.
division to subtraction. It's
Yeah.
very useful.
Yeah. And in this case, we have seen if we change the frequency, output has some particular,
Correct.
response.
Correct.
So how do you characterize that? Can we capture that also somehow in this transformation?
So clearly, in some way or other, the frequency should be part of the transformation.
Correct.
That's what you are pointing out.
Correct.
I think I see it.
Correct.
Because we know that, like for example, when we even solved the first equation, when we did dv by dt,
Correct.
c dv by dt,
Yes.
when v was, for example, cos omega t,
Yeah.
we basically got omega times minus sine omega t when we differentiated, things like that. So clearly there is a function of frequency.
Correct.
So I understand. So what you are saying is we need to transform from the time domain to some other domain.
Yes.
Maybe frequency domain?
Frequency domain. Yeah.
Something like that.
Yeah.
Okay.
So I was going through the textbooks,
Uh-huh.
seen some transform called Laplace transform.
Yes, yes. I think there was a famous mathematician called Laplace a few hundred, 200-300 years ago. I think it is named after him. I think he discovered this transform.
Oh. So whether it was discovered for, I mean, he has proposed for circuit analysis or?
No, I think he proposed it as a mathematical, identity.
Okay.
Actually, I think Laplace transform is used not just in electrical engineering.
It's for?
A lot of engineering disciplines use Laplace transform. Because like you said, no, it is like using log and antilog.
Okay.
It is not just one area of science or engineering uses it, everybody uses it.
So we are just using that to analyze our circuits also.
Correct. Well, till a few days ago, we were talking about in-phase and quadrature phasors, right?
True.
We were using complex numbers.
Yeah.
But we used complex numbers only because they were at 90 degrees, no?
Yes.
We said one is the real axis, other is j omega axis.
Yes.
And we have studied complex numbers. We know how to work with them, so we use that. So this is like that.
Okay. So if we have a time domain signal, a signal in time, let's say that is f of t. So the Laplace transform says, I mean, if you do that, then usually it is represented as f of s.
Yes, correct.
So how do we get f of s? I was looking at the definition. So what it says is f of s is you integrate from 0 minus to plus infinity f of t. You will multiply f of t with e raised to minus st.
Oh, okay. Okay, that is okay.
Yeah, dt. So now we see something new. Yes.
S. Actually, what is 0 minus?
Oh, 0 minus. 0 we know.
0 we know.
So I think in the circuit analysis, sometimes we may have, let's say you were talking about this RC circuit.
Yes.
So we see, or for example, let's say this signal Vs instead of sine wave, let's say it's a waveform like this. This is time t equal to 0. Until 0, it is 0.
Okay.
And then it goes, let's say, up.
Okay.
And from then onwards, let's say it's constant.
Okay. It's a step.
It's a step.
Okay.
So let's say this is a 1 volt. So till 0, it was nothing. I mean, it was 0. That is 0 minus. So because at 0 exactly you had this transition.
You have that. So you have to define the value.
Somehow we need to express what happens just before 0.
Just before 0.
Or what happens just after 0. This is also applicable, I think, when you have a switch also.
Switch, correct. So now I understand. So just before 0 would be 0 minus.
Correct.
So just after 0 would be 0 plus.
Correct.
Okay.
So let's say we have some source here, DC source also. Then let's say I have a switch and R and C. And if I am controlling this switch, if I say I'm closing this switch using this signal.
Okay. So the switch is closing at t equal to 0 exactly.
Yeah.
Okay.
So at 0 minus, let's say this capacitor had some charge stored in that. I want to somehow represent that. So in those conditions, this becomes, I think, more useful. So what was there just before your action and what was there just after that?
Understood. So when the signal changes suddenly, you don't want to define the integral starting point at that point.
Correct.
So you want to do it at slightly to the left of it.
Correct.
Understood.
Correct. Oh, and then what about this S?
S. What is that S? So this is, so you are saying that if you have a function small f of t,
Yeah.
the Laplace transform is capital F of s.
Capital F of s.
Ah, okay, okay. Okay. S,
So
see,
yes, they say
Uh-huh.
it's some sigma plus
Okay.
j omega.
oh, complex numbers again.
Yeah,
Okay.
yeah.
Okay.
So this has got some real part
Okay.
and an imaginary part.
Ah, okay, okay. I see. Okay.
Hmm?
Understood. Okay.
So real and
So it seems like
Yeah.
you are taking that a time domain function f of t
exactly
and mapping it onto some real and imagine complex plane, something
Into a
like that,
complex
right?
plane.
Into some complex plane. So if I imagine you showed no like this some unit step,
Correct.
or if I have a sinusoid,
correct.
it seems like the final function is f of s,
Hmm.
and so it can be drawn or represented in some
Some other domain
domain, which of course
which has a real and imaginary
real
axis.
and imaginary axis. Okay,
It's a
Understood.
bit difficult to visualize.
it's a little bit more abstract right
correct,
now, no?
correct.
Okay, okay,
But what we are looking at is whether this can be used to analyze our circuits.
correct. Okay,
And see, every time if I have to do this e power minus st, f of t e power minus st dt integral from 0 to infinite, personally I don't like it, integrating every time.
correct, correct.
But what we realize, I mean, we may see soon that for most of the signals f of t, there are some transforms available,
Okay.
or
This is
people
like
have
your-
done it already.
This is like your log tables.
Correct.
You already have log tables already tabulated.
Correct.
So if you know, you can just look at the table, use
Yes.
it to solve your problem.
Yes.
Mm.
So use that transform and then represent in the algebraic form like you mentioned,
Okay.
solve easily,
Mhm.
then get back to time domain.
Time domain. Okay.
So you have to do some inverse transform also.
Okay. Okay. I see.
Hmm?
Okay.
And for this, I think there is also some condition
Mm. Okay.
for a signal f of t to be, to represent in or to transform into Laplace domain.
I think there is some condition using the magnitude of the function or something.
Yes,
right?
yes. So what it says is this f of t, magnitude of that, you integrate from 0 minus to infinite,
Okay.
e power minus sigma t
Ah. Okay.
dt should not be infinite. It should be less than.
It should be less than infinite. It should be
less than.
finite.
Correct.
Mm.
Correct.
Okay.
And it seems for most of your application, this is,
This is valid.
yeah, because you are multiplying with e power minus something
Mm.
with respect to, I mean, e power sigma t. So over time, sigma t, I mean, e power minus t is going to reduce with respect to time.
Correct. Correct.
Something like this.
Correct.
So definitely, this works out. This condition is mostly satisfied
For most practical
for most practical
situations.
So for most of our electrical circuits, I think we don't have to check whether this is possible or not.
Yes. Correct.
Mostly, and transforms are available. So, but for the definition point of view, it's good to know there is a condition
Correct.
that we need to satisfy.
Correct.
Right? So mostly what we need to remember is this.
Mm.
Yeah, maybe the
Okay.
correct. So what shall we do next? So maybe we will pick up this signal
Definitely.
and see is there a how to represent that as f of s.
Definitely.
By the way, for Laplace transform, there is also a symbol that is used, no?
Yes, it like a kind of a flowery L is what I think
will
of
try
it.
that. I will try that.
Okay.
So something like this.
Something like that. Correct. Something like this. Yes.
Yeah.
Correct.
And then they say Laplace transform of
Correct. Of f of.
f of t.
Yes. Correct. Correct.
Okay.